Good morning, everyone, and thank you for joining us. The topic of this month's Bic Gardner Web Seminar is Viscosity Basics. Just for a few introductory tasks, hopefully you have all been able to join into the platform's audio. You can connect either via your computer or by calling in on your phone. Of course, if you haven't already, then nothing I say is going to help you, so I'll just leave this slide up for a few seconds, and hopefully any stragglers will be able to join us as well. Okay, your speaker today is this dashing fellow, myself. My name is Corey Cohen, Application Specialist with Bic Gardner USA for going on about a decade now. I specialize in customer education and technical training and advise on best measurement practices. So just some general information about the web seminar today. The mute setting has been initiated by me, the speaker. It's not that I don't like you guys, it's just this way I get to tell as many yo mama jokes as I want, and there's nothing you can do about it. If you have any questions that I have not answered by the end of the web seminar, please enter them into the chat function, because at the end we will have some time for a brief question and answer session. And yes, you will all be sent the presentation via email as a PDF file after the presentation today. So without further ado, I will commence our discussion on viscosity and viscosity measurement methods. So viscosity. What is viscosity? So some possible descriptions for viscosity are a fluid's internal resistance to flow, the opposite of flowability, so the more freely a liquid flows, the less viscous it is. You can call it the fluid's resistance to deformation under shear stress, a fluid's internal friction, or you might even refer to it as the toughness of liquids. So as with any type of measurement, it's important to control for as many variables as possible in order to get repeatable, comparable measurements. So relative measurements when it comes to viscosity will depend on things like the sample temperature. Typically, the higher the temperature of the liquid, the lower the viscosity. So in order to get comparable viscosity readings, you need to control for the temperature of your liquid. The measuring instrument you use is going to have a significant impact on the results that you get. The sample volume is important, and other aspects of the sample preparation. It's important to keep as many things consistent as possible. So viscosity. Let's define a few terms here. Shear rate. Shear rate is the difference in speed between plates or two surfaces divided by the distance between those plates or surfaces. And so generally one surface will be in motion, the other will be stationary, and the shear rate is the difference in their speeds divided by the distance between them. And then we have shear stress, which is the external force acting on a surface parallel to the slope or plane in which it lies. So here we have this nifty little diagram or graphic here, as well as the equations for shear rate, which again is the difference in velocities between plates or surfaces divided by the distance between the plates. And in this case, the moving plate in this graphic is the paintbrush, and there we go, see, it moves. And the stationary plate is the substrate. And so we have shear stress, which is calculated as the shear force divided by the area. So essentially the force being applied on the coating by the paintbrush divided by the area of the brush that's in contact with the coating. And from those two things, shear stress and shear rate, we can calculate the dynamic viscosity, which is the shear stress divided by the shear rate. And also the kinematic viscosity, which is the dynamic viscosity divided by the density of the liquid. So we have two forms of viscosity, one that takes the liquid's density into account and one that doesn't. So dynamic viscosity is the ratio of shear stress to the shear rate, and is also known as the inverse of fluidity or flowability. So as I mentioned before, the less a liquid flows, the more viscous it is, and vice versa. And kinematic viscosity, again, is the dynamic viscosity divided by the density of the liquid, and is directly measurable with devices such as flow cups, where the density has an influence on the flow time. So next, let's define some units for dynamic viscosity. Dynamic viscosity can be expressed in units of poise, with one poise being equal to 1/10 of a Pascal second. Pascals, by the way, is a unit of pressure, so force divided by area. A centipoise, in turn, is, of course, a hundredth of a poise, or 1 millipascal second, or 1,000th of a Pascal second. And a Pascal second can be further broken down into Newton seconds per meter squared, or kilograms per meter second. So a few different ways you can express that. Now for kinematic viscosity, that's given in units of stokes or centistokes, where a centistoke is a millimeter squared per second, and a stoke can be expressed as a centimeter squared per second, or a poise centimeter cubed per gram. So remember, we're taking the dynamic viscosity and dividing it by the density. So when it comes to viscosity, we like to categorize liquids into a couple different categories. One is Newtonian liquids, which include water, mineral oil, silicone, honey, and glycerin. And then we have non-Newtonian liquids, which come in a few different categories. We have thixotropic liquids, which include most coatings. We have pseudoplastics like inks, shampoo, and hand lotion. We have plastic liquids like ketchup and mayonnaise, and dilatant liquids like cornstarch mixed with water, ceramic slurry, or cement. So what exactly is a Newtonian liquid? A Newtonian liquid is one where the viscosity does not change with changing shear rate. So no matter how much shear, how much force you apply to Newtonian liquids, the viscosity remains constant, which of course you can see here on this in this graph on the left. And that also means that the ratio between shear stress and shear rate remains constant, which you can see from this graph on the right, which has a slope of 1. Now we're looking at some graphs of the behavior of a non-Newtonian liquid. And a non-Newtonian liquid is one where the viscosity does change with changing shear rates. So for example, in this example here, we have a pseudoplastic, and pseudoplastics decrease in viscosity with increasing shear rate. So if you remember, one of our examples of pseudoplastics was hand lotion. And so if you think about hand lotion sitting in a tub, it doesn't flow very easily. If you were to, build a little mound of hand lotion or make some sort of indent in it, it would more or less stay in place. It wouldn't flow like spilled water or, say, your mama's back sweat. So it's somewhat viscous. But lotion doesn't give much resistance when stirred. It stirs very easily because the more shear stress you apply to the liquid, the thinner or less viscous it becomes. This means that as shear rate increases, the shear stress does not increase at the same rate, which you can see here in the graph on the right, and that results in a decrease in the viscosity. So our next category of non-Newtonian liquids is thixotropic liquids. And thixotropic liquids, like pseudoplastics, they also decrease in viscosity with increasing shear rate, but they're also time dependent. And that means that there's not a consistent relation between shear rate and viscosity. Viscosity can follow one curve with increasing shear rate and a different curve with decreasing shear rate. And it takes time for those thixotropic liquids to reset to their original viscosity. Remember, that encompasses most coatings, most paints and coatings. So we see a few different types of liquids graphed here. One we haven't talked about yet is dilatant liquids, and these actually increase in viscosity with increasing shear. And an example of this is cornstarch mixed with water. And this is actually a cool little experiment you can conduct at your home or in your office. You can take a bowl of cornstarch and mix in some water, and that's your dilatant liquid. And what you can do is you can take an object like a spoon or a butter knife, some sort of blunt object, and just sort of jam it into the cornstarch mixture. And if you do it really fast and provide enough shear, enough force, the viscosity of the liquid is going to increase dramatically to the point where it's like hitting a solid object if you hit it fast enough. So if you go nice and slow, you can take your spoon, you can dip it into that liquid nice and slow very easily. But if you jab it with that spoon quickly and you increase that shear rate, that shear force, you're not going to be able to get your spoon to the bottom of the bowl. It's going to be too hard, too viscous to do that. And we also see here our Newtonian liquid, which of course has constant viscosity with increasing shear rate, and our pseudoplastics that have decreasing viscosity with increasing shear rate. So here we have some examples of some various liquids. We have honey, we have mayonnaise, we have marshmallow cream. And here we see how each of these liquids responds to increases in the shear rate. So we have the blue line, which represents honey. And you can see that the viscosity remains constant with increasing shear rate. And that makes it a Newtonian liquid. We have the marshmallow cream, which is the black dotted curve. And we see that it's decreasing somewhat in viscosity with increasing shear rate. And this is one of our examples of a pseudoplastic. And then we also have the mayonnaise, and that's represented by the sort of pinkish dotted curve here. And the mayonnaise is decreasing, the viscosity of the mayonnaise is decreasing more or less linearly with increasing shear rate, and that places it in the plastics category of liquids. So here we have a fairly busy little graphic, and we can see a curve of viscosity versus shear rate for paints and varnishes. Remember that most coatings are going to be thixotropic, meaning the viscosity decreases with increasing shear rate, as we see here. And included in this graph, we have several different applications for paints and varnishes, whether it's storage or application or what have you, as well as what the viscosity might be for each of these applications, and also which viscosity measurement methods or shear rates might be best for each application. So now that we have an understanding of what viscosity is and some of the different types of liquids when it comes to viscosity, we're going to move on to our talk of different types of viscosity measurement methods. So the first one we'll talk about are flow cups. These are cups with a defined geometry and volume. It has an orifice with a defined diameter, and these are usually defined by whatever standard test method is being followed, whether it's DIN, ISO, ASTM. The liquids flow through the orifice in the bottom of the cup through gravity, of course. And there is a laminar flow requirement, and that just means that as the liquid drains out of the bottom of the cup, it needs to be a smooth stream of liquid. It needs to be an unbroken stream. So if your liquid is so thick, so viscous that it's sort of dripping out of the bottom of the cup or coming in broken little bits, that is not suitable. It's too viscous for this type of measurement method. You need something that can flow smoothly, which is referred to as laminar flow. And the measurement is done by measuring the efflux time, which is just the amount of time that it takes for the liquid to drain out of the cup. So you measure that time in seconds, and then through an equation that's specified for each individual cup, you can convert that efflux time into an actual viscosity. And this gives you kinematic viscosity in cinestokes. Remember, kinematic viscosity, that's the one that does take density into account. So our flow cups are made of anodized aluminum with a stainless steel orifice. They're calibrated against standard oils. And as mentioned, they are for fairly low viscosity liquids only. If the liquid is too viscous, too thick, you won't get that laminar flow, that unbroken flow of liquid, and this type of measurement method won't be suitable. And as mentioned, in order to get good reproducibility, in order to get consistent results, you need to hold certain things constant. For example, temperature, and not just the temperature of the liquid before measurement, but the temperature of the cup itself. Because of course, if you take a hot or a warm liquid and place it into a cold metal cup, that cup is going to very quickly extract heat from the liquid, and you won't get the result that you're looking for. And also the Newtonian flow behavior of a liquid needs to be controlled for. So here's a comparison of different flow cups and how the efflux time relates to the kinematic viscosity. Now remember, these cups have different orifice sizes, so different cups, the liquid will flow out quicker or more slowly depending on the orifice size. And so for the thickest liquids, in order to maintain that laminar flow requirement, you'll want to use a cup like the ISO 6 millimeter that has a larger orifice, so you can get a smooth flow of liquid out the bottom. And for less viscous liquids, you'll want something with a smaller orifice so that the liquid doesn't flow out too quickly, and you can get more precise results. So our next category of viscosity measurement tool, we call them bubble viscometers, or sometimes they're referred to just as bubble tubes. And these are liquid standards in sealed glass tubes. You have one tube, an open tube that you can place your sample in to be measured. There are 4 different tube sets with the standards have viscosities ranging from 5 up to 100,000 centistokes. So we're in centistokes, which again is kinematic viscosity. So again, we're dealing with measuring viscosity through the flow of the liquid. The density does come into account, and so we're measuring the kinematic viscosity. And the measurement principle is that the time required for an air bubble in the liquid to rise is directly proportional to the viscosity of the liquid. And so the faster the bubble rises, the lower the viscosity. So the procedure for testing your viscosity using these bubble tubes or bubble viscometers, you pick the 4 standard tubes that you think are closest in viscosity to your sample. So this is a comparative test. You're comparing your liquid or the bubble rise in your liquid to the bubble rise in these standards. You want to pick the closest ones to your liquid. You fill your sample tube with liquid, of course leaving a little bit of space for a bubble, and it'll leave as a marking on the tube that shows you how much space to leave. And then you close it tightly with a cork, because you're going to have to turn that tube over to do the measurement, and you want that cork to be nice and tight so your sample liquid doesn't flow out. And so you insert the 4 lettered tubes, the bubble viscometer tubes with the standards in them, along with your sample tube into the tube holder, which is that little holder you see at the bottom right with that black handle. And then you turn the holder over, and so all of these tubes of liquid are being turned over at the same time, and you're going to visually compare what letter of bubble viscometer best matches the rise time of the bubble in your sample. And so, again, you need to hold as many things constant for the measurement as possible in order to get repeatable, consistent, comparable results. And so, for example, temperature is very important to control. Even a difference as small as 1 degree Celsius can result in as much as 10% error. And the verticality of the bubble tubes is also important. You want them to be perfectly vertical. As much as a 5 degree deviation in that verticality can result, again, in a 10% error. And that brings us to our rotational viscometers. Some examples of these would be cone and plate viscometers, Krebs viscometers, or rheometers. So back to our definitions of shear rate and shear stress. We've seen these before. So shear rate is the difference in speed between plates or surfaces divided by the distance between the plates. And for rotational viscometers, the shear rate can be changed by the rotational speed of the spindle. So the spindle is the moving plate or the moving surface, and then the vessel or the container that you're testing your liquid in is the stationary plate, and you can vary the shear rate by varying the speed at which that spindle spins. And then, of course, the shear stress is the external force acting on a surface parallel to the slope or plane in which it lies. And for rotational viscometers, that's going to depend on the spindle's dimensions, the sample volume, and the sample container, how big the sample container is. So for rotational viscometers, the liquid to be measured is sheared between 2 surfaces. Again, that's the spindle and the container of the liquid. One surface is stationary, the other is rotated. Spindle is rotated, the container is stationary. And the measurement can be made either by setting a constant speed and measuring the torque applied on the spindle, or vice versa. So one specific type of rotational viscometers, it's called the Krebs Criscometer. This is primarily used for architectural coatings. It has a spindle with a paddle design. You can see that in that graphic to the right, that little spindle sticking out from the viscometer unit, and has those 2 little offset paddles. The rotational speed is fixed at 200 RPM. And the range of viscosity this is capable of measuring is between 30 and 5,200 centipoise. So with rotational viscometers, we're now measuring dynamic viscosity. The measurement output is in Krebs units, grams, or centipoise. So these units, the Krebs viscometers, the idea behind this is basically that a lot of the measurement parameters are fixed. The speed is fixed. There's only one spindle. And so the results you get when using a Krebs viscometer tend to be very comparable with other people or other companies or locations that may be also using a Krebs viscometer, without having to make sure that you control for things like the speed, because it only comes with one speed and one spindle. So it's kind of a very simple viscosity test for a rotational viscometer with a lot of the parameters preset so that you have consistent, comparable results. And then we have other rotational viscometers that have a selection of spindles. These can measure anywhere from 1 to around 100 million centipoise. They come in 3 different versions generally, an L, an R, and an H. The L version is for relatively low viscosity liquids, and that can measure in the range of 20 to 6 million centipoise. The R model is for medium viscosity liquids, and it can measure from 1 to 13 million centipoise. And the H is the high viscosity model that can measure from 200 up to over 100 million centipoise. And so the actual difference between these 3 units, it has to do with basically 2 things. One is the set of spindles that you're getting. The L, the R, and the H each come with a different set of spindles. The higher viscosity versions come with larger spindles that increase the shear stress, or the shear rate, I should say. No, I think shear stress is correct. And some of the accessories we have available for these rotational viscometers include, we have a low viscosity accessory for measuring samples with viscosity all the way down to 1 centipoise, which, by the way, is the viscosity of water. We have a small sample adapter for measuring low volume samples from 8 to 13 milliliters. Generally, with these rotational viscometers, you need maybe a few hundred milliliters of liquid. But with the low volume adapter, you can measure as small as a small volume as 8 to 13 milliliters. And also non-flowing samples. So there's an accessory for measuring very, very viscous non-flowing liquids such as peanut butter. That's the classic example of this. It's called, I believe, the heliopath stand is what we call it. It basically makes the spindle move through the liquid or the peanut butter, whatever it is, in sort of a helical motion. So if you think of trying to stick a spindle down through peanut butter and that spindle starts spinning, that spindle is very quickly going to push all the peanut butter away from it, and pretty soon it's just going to be spinning through open air, and then you're not measuring anything. And so that helical motion of the spindle that you get with this accessory is going to make it so that spindle is always in contact with the liquid, and so you can measure non-flowing liquids such as peanut butter. We also have accessories for samples that need to be heated during measurement up to 300 degrees Celsius. So these would be for things like waxes that may be solid at room temperature, but if you want to measure the viscosity of the liquid wax, you of course need to heat it before taking your measurement. The next example of a rotational viscometer is the cone and plate viscometer. These are for high shear measurement applications. We have the CAP 1000, and this comes in both a low and high viscosity version. They measure at just 2 different speeds. The 1000 version only comes with 2 speeds, 750 and 900 RPMs. And it's kind of interesting why those 2 particular speeds are chosen. And it's basically because when the first cone and plate viscometers were developed, there was no voltage control. There was no voltage converter for the input electricity. So if you took that cone and plate viscometer and plugged it in here in the US or in North America where you're getting 1 voltage, it would spin at 1 speed. If you plug it in over in Europe where it's getting a different voltage, it would spin at a different speed. And those 2 speeds happen to be 750 and 900 RPMs. But we also have the CAP 2000, which also comes in a low and high version, and these do have variable measurement speeds that you can set anywhere from 5 to 1000 RPM. And where the CAP 1000 is capable of measuring up to 10,000 centipoise, the CAP 2000 can measure up to about 1.5 million centipoise. And for low shear measurement applications, We have the 1/23rd cap 1000. It's called 1/23rd because the torque spring is 1/23rd the force, or the coefficient of the spring is 1/23rd of the cap 1000 and 2000. And so the 1/23rd cap 1000 has a fixed speed of 100 RPM and can measure anywhere from 22 to 220 centipoise. And then we have the cap 2000 version with variable speed selection that is capable of measuring up to 4,400 centipoise. So remember, these are for relatively low shear applications. It also comes in a low temperature version and a high temperature version, and the low temperature version is capable of measuring, and you can set your liquid to be measured at anywhere from 5 to 75 degrees Celsius. The high temperature version ranges from 50 to 235 degrees Celsius. So again, this is a good instrument if you have something that needs to be heated, such as a wax. These units can do the heating and take the measurement for you. Another benefit of these cone and plate viscometers is that they require very, very little volume of liquid in order to measure, less than 1 milliliter. So some of the benefits of our Visc rotational viscometers are the instruments can actually be calibrated by the user. They do, of course, come calibrated from the factory, but unlike with our competitors, if you find that the viscometer is out of calibration, you can actually calibrate it yourself in your own lab using a standard oil rather than requiring that it be sent in for a calibration. But we do, of course, offer calibration and certification services at any of our Bic Gardner service points, and possible on-site recertification, which we hope to restart as soon as possible once we are done with this pesky virus. Another benefit is that they are comparable to Brookfield models, meaning that the spindles are actually interchangeable. You can use Brookfield spindles in Visc instruments, and the results that you can expect to get from the Visc models will match very closely with the results that you will get with Brookfield models. So here we have this comparison of methods. This is sort of a summary of what we've talked about. We have flow cups and dip cups. These are where you have a cup of a defined volume and you measure how long it takes your liquid to drain out of the bottom of the cup. These are for Newtonian fluids only, and they measure the kinematic viscosity, the density-dependent viscosity. They are only for low viscosity liquids due to that laminar flow requirement. And they are only for comparative measurement between batches. So we might say that this is sort of a quick and dirty method for comparing viscosities between samples, between batches. We also have our bubble viscometers, which again are only for Newtonian fluids. They give you the kinematic viscosity, and these, due to the measurement method, they are only for transparent fluids, because of course you have to evaluate the rise time of that bubble in your sample, and in order to do that, you need to be able to see the bubble, so it can only work with transparent fluids. And then we have our rotational viscometers, which come in several different varieties. These are the much more versatile and much more precise viscosity measurements. They can measure both Newtonian and non-Newtonian fluids. They can measure dynamic viscosity, and if you know the density of your liquid, you can input that into the viscometer, and it will also tell you the kinematic viscosity. The continuous rotation of that spindle allows measurements of time-dependent fluids. Remember, those are our thixotropic fluids, which encompass most paints and coatings. The shear-dependent behavior can be analyzed, so you can vary the shear of the application of the viscometer, and you can analyze the behavior of the viscosity of your liquid with changing shear, and so you can create those those curves that we saw before, the behavior of the liquid at different shear rates. And the measurements tend to be highly reproducible. So here we have an overview of different methods, which industries and markets use them, different applications, advantages, things like that. I won't bore you by reading this entire table, but again, you will be getting this presentation emailed to you, and so you can refer to this table if you'd like to. All right, so that does it for today's presentation on viscosity. Just a few cleanup announcements. This right here, I know what you're thinking, but no, this is not the 2020 roster of the New York Knicks. This is actually Bic Gardner's technical service team, including those of us both here in the U.S., in North America, as well as our colleagues over in Europe. And you can reach out to us at any time. You don't have to wait for a web seminar to have your questions answered. You can see that all of our email addresses and phone numbers are included here. We'd love it. If you have any questions, feel free to reach out to us, and we can discuss your application and answer your questions and help you in any way that we can. Our next monthly Bic Gardner web seminar will be on color systems for solid and effect colors. And so this will involve improved color difference equations for different types of coatings. Again, when there's not a killer virus on the loose, we do like to provide on-site seminars to customers who request it. And this is where we can go to your location. We can bring whatever instruments with us that you'd like, not just viscosity, but we can bring our color instruments and our gloss instruments and haze instruments and whatever you'd like, and we can customize a presentation just for you. We do have a new website, byk-instruments.com. Give it a look. And on YouTube, we have several videos available that show our instruments in action. So if you want to see how these instruments are actually used, how to operate them, you can visit them at youtube.com/user/BIC-video, or just go to YouTube and type in BIC. And lastly, we would love to host you at one of our sites. I'd hate to repeat it, but again, we are not doing this right now, but when the pandemic is over, we'd love to have you at one of our locations, either our North American headquarters, which you can see at the top there. We're located right between Baltimore and Washington, D.C., so plenty to do around here. If you happen to be in the area, be sure to stop and visit us around. And also our production facility at our headquarters in Geretsried, Germany, which you see at the bottom left there. My colleagues over in Germany would love to host you. They can show you around, show you our production facilities, as well as get you some lovely German beer, which I must say is quite excellent. So that does it for our presentation, and now I will take some questions. Give me a minute to look at the Q&A. So somebody has asked if the viscosity is in date. Take it that you mean one standard that you can use to test the calibration of your rotational viscometer, or any viscometer. You can use those to test cups in your bubble tubes as well. The question is then a need to get the the certification sticker. Okay. Really, it depends on your own specific requirements. Some companies are required to keep very strict records. Sometimes their customers require them to, make sure that all of their instruments have that certification sticker, particularly when you're dealing with things like pharmaceuticals or, government contracts. Sometimes those things are required. So it really depends on your own requirements. Sometimes you need to have that sticker that says it's in the certification period, and sometimes you don't. So one question is why viscosity values are not stable. I take it you mean perhaps across different measurement methods, which is true. You are going to get different measurement results depending on the method that you use, and that will have to do mostly with things like the differences in the shear rate and the shear stress. It's very I don't want to say subjective, but the results that you get are going to be very dependent on the measurement method. So if you want comparable results, you need to make sure to use the same method every time, whether it's the flow cups or the rotational viscometers, and again, try to keep as many of those parameters as possible consistent, like the sample temperature and the rotational speed. So someone mentioned that they're using a Krebs unit viscometer and asking why the viscosity drifts over time. Now, remember that Krebs viscometers are typically used for architectural paints, which fall in the fixotronic category, where the viscosity can change over time. Still, that being said, if you let it spin at a consistent speed for long enough, the measurement stabilize. So if you're getting inconsistent results, it may be that you're not letting it stabilize for long enough, or maybe you need to pick a specific time to measure the viscosity. Say let it spin for 30 seconds and then take the viscosity at 30 seconds. That way you can get consistent results across measurements. Are there any correlation charts between L and R measurements? There are not. Again, different measurement methods will yield different results. So you can measure the same liquid. There is some crossover plenty of crossover in the viscosity ranges that are measurable with the L and the R models of viscometer. So if you measure the same liquid with an L and an R, you likely will get different results. There is no conversion between the two. You just have to make sure to be consistent in your measurement methods. There is a conversion for different flow cups and dip cups. So if you have one dip cup that you're doing measurements with and you want to convert the results to match with a different type of cup, we actually have a free poster that we offer that does that conversion. So feel free to reach out to us and we can send you one of those posters at no cost to you. Several questions on being sent to this presentation. Yes, again, you'll get this presentation sent to you by email in PDF format. So someone asked, what is Newtonian fluid and non-Newtonian fluid? Just again, Newtonian fluids are liquids where the changes in shear rate are not going to affect the viscosity. You'll get consistent viscosity out of the shear rate. So the relation between shear rate and shear stress is consistent, whereas non-Newtonian fluids, as you increase the shear rate, the viscosity change will either increase viscosity with increasing shear rate, such as the example with the cornstarch mixed with water, or it might decrease with viscosity with increasing shear rate. Viscosity will decrease with increasing shear rate, as with the hand lotion example. Okay, it looks like that is all the questions I can answer right now. I do recognize that there are some questions that have been asked that I have not been able to get to, and that's just because I'd like some time to maybe do some research and give you a more thorough explanation. But again, you will get all of our contact info for the BIC technical service team, including my own, with this presentation. And so I encourage you, if I've not answered your question, please reach out to us. We'd be happy to discuss it with you and provide a more thorough answer when we can. Okay, so it does look like we have no more questions, and I will go ahead and conclude the web seminar. Thank you all for coming. I hope you have a great rest of your day.